here we're going to talk about the chain rule. Now, the chain rule is definitely one of the most, if not the most important result we're going to cover this semester. And the chain rule allows us to take many more derivatives than we can take simply using the chart of derivatives. So before you listen to this video, be sure you have a good amount of practice working on derivatives that require only the chart, and lecture 2.2, because that is very much a prerequisite for what we're going to do here. Now, the chain rule allows us to take derivatives of compositions. We don't necessarily have to think of them in terms of compositions directly, but we can use these to take derivatives of compositions. When I go through chain rule examples, I have thought probably 0 times, ooh, this is a composition. I more just look at the function and think of it slightly differently. We'll see that as I go through some examples. But the notation for the chain rule looks like this. The derivative of a composition, so of f of g of x. This is one of those many, many things where I find unlined paper much more useful than, much more useful for than lined paper, because it allows me to properly size my parentheses. But the derivative of a composition, f of g of x, is given by f prime of g of x times g prime of x. So we have a composition. The derivative is given by f prime of g of x times g prime of x. I always like to think of chain rule in terms of an outside function and an inside function. The derivative of a composition, which is an outside and an inside, is given by derivative of outside, leaving the inside alone, times derivative of inside. So derivative, I didn't write leaving the inside alone, but as we do the examples, we'll see what we mean by all of this. Derivative of composition is the derivative of the outside, leaving the inside alone, times the derivative of the inside. An alternative notation, which is quite useful, uses the fractional derivative notation. dy dx equals dy du times du dx. Now, we'll go through some examples where we introduce a u to help us, and choosing that u corresponds to viewing an inside or seeing an inside function. This notation, this fractional notation, is useful for understanding many things. The mathematician Leibniz, Gottfried Leibniz, used this notation in his discovery of calculus. And these do not necessarily act like fractions. Sometimes the fractional notation can be thought of as fractions, but in general, derivatives are not fractions. This is one example where it happens to function very nicely as fractions. If you take Calc 3, where we have more than a function of more than one variable, so instead of just a function of x, you have a function of multiple variables, the chain rule will not look like a fraction. Well, it will look like a fraction, but it won't act like a fraction. If it did, 1 would equal 2 in Calc 3. But for our purposes, thinking of these as behaving like fractions is useful for helping you set up some chain rule examples. So let's do some examples. These are all going to be find dy dx. I'm using dy dx because we will do with the alternative notation, we will introduce a u and do a u substitution. So find dy dx. Let's start with y equals sine of 2x. We can't do this derivative using the chart because of that 2. But what can we do? We can view this as a composition of functions. It is sine of 2x. So our f would be sine, our g would be 2x. Alternatively, we could view it with an outside-inside. Let's let's do the outside inside first, and then we'll do a u substitution. So the chain rule says derivative of f of g of x is f prime times g prime. F prime of g times g prime. Well, here our f is g. Here our f is sine. So we need the derivative of sine. Well, the derivative of sine is cosine. This tells us here to leave the inside alone, leave the g alone. So leave 2x alone, but then multiply by the derivative of that g, of that inside, of 2x. Derivative of 2x is 2. So derivative of sine of 2x is 2 cosine of 2x. So notice what we did here. We did the derivative of sine, and we left the inside alone, and then we multiplied by the derivative of the inside. So here, our outside function, our f, is sine. Our inside function, our g, is 2x. And we followed the chain rule. F prime of g times g prime. Using the other notation, this marker isn't working well. I'm going to use a different one. Using the u substitution notation. So I'll say alternative. Let's spell alternatively. Alternatively, we could use a u substitution. And in many ways, when you're first learning derivatives, doing a u substitution is useful, especially for more complicated ones. When I was doing these, I learned them with u substitutions. We have y equals sine of 2x. The goal of a u substitution is to allow us to use only things in the chart by making an appropriate substitution. And here we observe 2 is in the way. So we take this 2x term, we'll say let u equal 2x. Well, what happens if we let u equal 2x? Well, this y is now a function of u. And u is a function of x. Our goal, remember here, is to find dy dx, which can be broken down into dy du times du dx. Meaning we need y to be a function of u and u to be a function of x. Well, we have y as a function of u and u as a function of x, and we can take both derivatives using the chart. Du dx, the derivative of u with respect to x, is just 2. Dy du, y equals sine of u, derivative of sine is cosine. So dy du is cosine of u. So here, dy dx is just the product of these two. Dy du, so cosine of u, times du dx, times 2. And we want our final answer to be in terms of x, so we just replace u with, in this case, 2x. And I like writing the 2 in front. So here, we let u be our inside function, the thing preventing us from using the chart, and then we take the two derivatives and multiply them. And of course, you can see that these are, in fact, doing the same thing. But in general, what did we do here? We have a function, sine of something. The derivative of sine of something is cosine of something, times the derivative of this inside. And thinking of it like that is very convenient as we learn chain rule. So let's do some more. Let's do this next one, and you can compare it to the first one we did. Find dy dx. Y equals, I'm going to write it here so it's all on one board. Sine of 4x squared I guess it's not on one board, plus 7x. I think this is like the 4th time I've used 4x squared. I don't even like the number 4 that much. Find dy dx here. Well, I'm just going to give you the answer and then talk about it. The answer is very similar to the previous line of thought. Dy dx is cosine of 4x squared plus 7x times 8x plus 7. Now this marker is running out too, so let's get another. Now where did this come from? Well, a couple ways you could see it. Derivative of a sine function is a cosine function. Leave the inside alone, then multiply by the derivative of the inside. So compare this to the previous one where the inside was 2x. The inside was 2x, this was a 2x, and this was a 2. But here, we've done more with the inside. What would the u substitution be if you wanted to do a u substitution, which you should write out the details. I'm not going to write out the details because it's very similar to the last one. What u substitution would you use? Well, let u be the inside of this. 4x squared plus 7x. And then you can check dy du is, again, cosine of u. Du dx is 8x plus 7. And then dy dx is cosine of u times 8x plus 7. And u equals 4x squared plus 7x. Let's do one more, just like that. Y equals sine of... This is what I should do. I should put y here. Y equals sine of... Let's do tangent of x. Sine of tangent of x. Well, what is this? What is this derivative? Let's do a u substitution. And then we'll compare it to the previous two. What would our u substitution be? Well, again, this function here, in its most basic sense, is a sine function. So here we're going to let u be the inside, tangent of x. Well, what happens if we do that? Well, again, y is just sine of u. So what's dy dx? dy dx is dy du du dx. Again, very important formula. dy du du dx. Again, they do not act like fractions. The derivative is not a fraction, but the notation is convenient. Well, what's dy du? Y is sine of u. So dy du is cosine of u. Y is a function of u. We're taking the derivative with respect to u. And what's du dx? Well, u is tangent of x. So du dx is the derivative of tangent of x, which is secant squared of x. And we don't want u's in our answer, so we have cosine of what's u, tangent x, times secant squared of x. And again, you can compare this to the first two examples. All of them take the same form. The derivative of sine of something is cosine of that same thing times the derivative of that thing. And that's what the chain rule is doing. It allows us to take derivatives of compositions, derivatives of functions where we have an outside and an inside. So we saw some examples with trig, and that's not the only thing we can do with these. Let's do a few more examples. How about y equals 9x to the 4 minus 7x to the negative 6. If I just left it like this, you would not need chain rule. to the, what's a good number? Let's see, 36, 42. Let's make it 23. So you could multiply that all out using the 24th row of Pascal's triangle. Or you could use chain rule to find the derivative. We have here, what is this? This is a function to the 23rd power. We know how to take the derivative of something to the 23rd power. What's the derivative of x to the 23rd? 23x to the 22. But here, this x is a lot more than just an x. When your x is a lot more than just an x, you can use chain rule. So let's do that. Let's let all of this be a u. So let 9x to the, or I guess I've been saying let u equal 9x to the 4 minus 7x to the negative 6. Well, we have our y, we have our u. Y as a function of u is now just u to the 23rd, and we can now use this chain rule that I erased, or the power rule that I just erased. So what do we have here? dy dx is dy du times du dx. What's dy du? Well, y is just u to the 23rd, so dy du is just 23 u to the 22 using a power rule. What's du dx? Well, here we just have a couple power rules. 36x cubed, positive 42x to the negative 7. Now this answer doesn't have only x's. We have to get rid of the x's, but we have a function to the 23rd. Well, I'll write the answer and then say what I was about to say. So we have 23 of these to the 22 times 36x squared minus or plus 42x to the negative 7. Sorry, I had to squeeze that in there. I didn't realize how big I was writing. But of course that's just this. So let's look at how we could get this answer in one step. We have here a function raised to the 23rd power. Well, a function raised to the 23rd power. Derivative would be, let's look at our answer. Use the power rule. 23 of them to the 22. 23 of them to the 22. But then you multiply by the derivative of the inside. So just given a thing to the 23rd, the derivative is 23 of them to the 22 times derivative of the inside. In your work, you could do it in one step, or you could write out the substitution. I definitely found the substitution very helpful when learning chain rule. What else could we do? What if we had this? Y equals square root of, I don't know, x cubed plus 2x. Well, you could remember that remark where we said the derivative of root x is 1 over 2 root x, but that's actually not necessary for something like this where we just need to find the derivative. What we can do to help us out a little is write this as a power. Square root is a thing to the half. So we have y is something to the 1/2. How can we do this derivative? Well, we do it just like we did before. The derivative, we have a function to the 1/2. So the derivative is a half of them to the 1/2 minus 1. Negative 1/2. But then times the derivative of this inside, which is 3x squared plus 2. So function to the half, half to the negative half, and then times derivative of the inside. Here, if you wanted to write out a u substitution, u would equal x cubed plus 2x. And also, this answer, when you get used to doing calculus, you oftentimes realize that looking at actual numbers is not as relevant as looking at just the variables. Or maybe I shouldn't say just the variables. Often not as important as looking at the general structure regardless of the numbers, I guess I should say. This answer and the previous one where that thing was to the 23rd look the same to me, because they are the same as far as the chain rule is concerned. Something to the half, something to the 23rd. The derivative is power rule. Half of them to the negative half, 23 of them to the 22. And then times the derivative of the inside. Let's do a few more. Let me look at my notes to see what kinds of problems I haven't done yet. Let's do, where am I? How about, a lot of trig in my notes. We already covered trig pretty well. Oh, okay, we didn't do anything with logarithms. How about y equals e to the x squared plus 4x minus 3. Y equals e to something. Well, the chart tells us how to do derivatives of e to the x. So let's make this look like that by letting u be our exponent. If u is the exponent here, this function y is just e to something, and we let u be that something. So y is e to the u. U is x squared minus 4x minus 3, or plus 4x minus 3. So I guess I was doing it down here. dy dx is dy du du dx. dy du is e to the u. Derivative of e to the u is itself. Du dx, derivative of this, well, that's just a polynomial. 2x plus 4. Don't have to factor that 2 out. So, replacing u with what u equals, we get our answer. Times 2x plus 4. Okay. Let's do a couple more. Well, before doing a couple more, let's just compare the original to our answer. So we have all those details explaining how we got to the answer, but let's compare the original to the answer. Derivative of e to anything is itself, but then you apply chain rule on that anything. Applying chain rule means taking care of a composition, or multiplying by the derivative of the inside. Derivative of e to the x is itself, and then apply chain rule. Let's do a few more. How about one with a logarithm? We haven't done a logarithm yet. Let's do log base 7 of sine. Let's do tangent of x. And let's not worry about simplifying anything right now. Log base 7 of tangent of x. This function is a logarithm function. We know how to take derivatives of logarithm functions. How do we take the derivative of a logarithm? Well, derivative of log x, 1 over x log base. So let's get rid of that tangent and replace it with u, because the tangent is in the way. If we let u equal tangent x, then y is just log of u with base 7. And now we can take the derivatives. So dy dx equals dy du dx. What's dy du? Well, page 2 of the chart, entry 3. 1 over u log 7 times the derivative of tangent. What's the derivative of tangent? Secant squared of x. And you could leave this as 1 over tangent x log 7 times secant squared of x. I'm just going to write it as one fraction. So secant squared of x over tangent x log 7. And this one actually does simplify a little, but don't worry about that. Does it? Yeah, because they're both divided by cosine. You can just leave it like that. Unless you're told to simplify, which I don't think I've ever actually said simplify a derivative. Let's do a couple more. How about a general exponential? How about 7, that's a good number, to the x to the 5th minus 3x. Yeah, that's good. 7 to the x to the 5th minus 3x. How can we handle this? Well, we know the derivative of 7 to the x is just 7 to the x log 7. But there's more than just an x there. So let's use the chain rule. More than just an x? Well, call that more than just an x. More than just an x, a u. So now y equals 7 to the u. So dy dx, I should probably just not erase that. dy du dx. What's dy du? Well, use the chart. 7 to the u log 7. You can't use the chart in a test. 7 to the u log 7. Natural log of 7 log 7. So here's dy du. What's du dx? Well, it's just 5x to the 4 minus 3. And of course, we don't want to leave u in our answer because we want full credit. Hopefully. So 7 to the x to the 5th minus 3x log 7. 5x to the 4 minus 3. And again, we can see this, as you get used to these, you learn how you can see these answers just from the beginning. Because you learn how to think of them as just 7 to something. Derivative of 7 to something? 7 to that thing, log 7. But then, chain rule says, multiply by the derivative of that thing. Let's do a couple more. Let's do 3 more, possibly 4 if I look at my list and realize there's something else we should do. Let's do this one. E to the 4, no, I don't want an even number. Well, I don't want a non-prime number, I should say. E to the 3x sine. We did a lot with sine. I mean, sine is really the best example for it. Sine of, yeah, let's leave it as sine. 7x. How do we take this derivative? Well, the first observation is, before we're even thinking of chain rule, we have a product. So we need to use the product rule. What's the derivative? I'm going to do this in one line. Well, in one step. I would recommend trying this before looking at my answer. I'm going to do it in one step, but you know it's a product rule. So see what you get and compare it to this answer. E to the 3x sine 7x plus 7 e to the 3x cosine 7. Where did that come from? Well, derivative, we did in maybe like the 6th, 7th, 8th example, derivative of e to something. Derivative of e to something is itself times the derivative of that something. Derivative of 3 is 3. Derivative of 3 is 0. Derivative of 3x is 3. So our product rule has that piece. Leave the second alone, plus the first times derivative of 7. Derivative of sine of 7x, it's a sine function, so its derivative is a cosine function. And then you multiply by the derivative of that inside. If in this you were doing, for each derivative you had to take a u substitution, u would be 3x for the first one, u would be 7x for the second one. I shouldn't have erased that. Well, I guess it doesn't matter. Let's do this. E to the 3x, sine of 7x, to the 54. How do we do this? Well, what is this function? A function to the 54th. That's all it is. A function to the 54th. How do we take its derivative? Well, the derivative of something to the 54 is 54 of them to the 53rd. Power rule. But then you multiply by the derivative of the inside. And I'm going to do a shortcut, intentionally, and say large star, where star, slightly smaller star, but we'll assume that similarity implies the same thing for this example, where star is what? What is star? Star is the answer to the previous example, because star is just the derivative of this inside piece, which we did in the previous example. How many more? Let's do one more. Let's see, what examples? I should do one like that. I did one like that. Oh, definitely that. Okay, 2 more. Let's do, yeah, 2 more. I forgot which 2 I'm doing. It's amazing. Oh, okay, those 2. I noticed throughout my 20s, I'm 29 now, I noticed that my ability to remember, well, my ability to immediately forget things got very strong throughout my 20s. Like I can remember many things from when I was like 15, 18, but I mean, through the 20s, it just, I don't know, I think that's when your mind starts to go. I mean, just look at that. I said, I'm doing these 2 examples. 1 second later, I remembered only one of them that I was doing. But that's okay. Cosine to the 4th of x. What is this function? It might not be obvious what the u substitution should be, especially if it's written like this. Another way of writing cosine to the 4th is cosine of x all to the 4th. And when it's written like this, it might be more clear what the u substitution should be. Because here, we just have a function to the 4th. So we're going to let that equal u to the 4th with our substitution, u equal to cosine of x. And now we can apply chain rule. So dy dx equals dy du du dx equals what? What's dy du? 4u cubed. What's du dx? Negative sine of x. And now we just want to get rid of that u, and I'm also going to put the negative out front because I don't really like how that looks. So negative 4, what's u? U is cosine. So cosine cubed of x, and then times sine of x, because I put the negative out front. So this is a function to the fourth. Its derivative is 4 of them to the third times the derivative of the inside. Let's do one more example with this one. What if I erased everything except this and that, and said, find the derivative of this function? No, sorry. This function. Whatever. I was being careless. Yeah, okay, 8. I was thinking 8 times 5 is 40, and I wouldn't have to erase anything. But I don't know what I was saying. What if I changed it to this function, just threw an 8 in front of it? Well, the answer would just be 8 of these, which is negative 32 cosine cubed x sine x. All the inside details that I erased, you'd have to put 8s on everything with a y. But that's more of just a side observation, that if you just throw a number on something, you have to remember that you need the number on the answer as well. Let's do one more. And this will actually lead us into an application. Natural log of x cubed plus 4x squared minus, let's make it positive, plus 7x plus 9. What would our derivative here be? I'm going to tell you. Unless you want to work on it yourself while paused. That 3x squared plus 8x plus 7 over x cubed plus 4x squared plus 7x plus 9. Where did that come from? Well, we know how to take the derivative of log of something. So what we could do is let that inside equal u. And then the answer would be 1 over u times the derivative of u. 1 over u is seen in this fraction. 1 over u is 1 over that times the derivative of u. So it would be 1 over that times that. So it's 1 over u times the derivative of the inside, which notice you can just write as a single fraction like that. This observation, I mean, I'm not going to ask find a general form for the derivative of log of u like this. But the observation that we can write this as a fraction is very useful and shows up a couple times throughout calculus. So these examples, these chain rule examples, they're all very important, and they definitely require a good amount of practice to get good at. And there will definitely be a question on the test, probably, I mean, with 50-point tests this week, probably at least 30 points. Do a bunch of derivatives, many of which will require the chain rule, some of which probably won't. But definitely practice these. There are a bunch of them on the worksheet, and there are a bunch of them in the textbook that you could try. It's very, very important.